We're recording.
We have started the record. So let me begin with the introduction of the Dr. Naohisa Sueishi. He's got a PhD degree just this March at Nagoya University. So he's a new postdoc. He's one of the young experts in the Exact-WKB and its application to physics. And he will give a talk on the Exact-WKB vs resurgence in semiclassics today. So please start.
Okay, thank you for introduction. And let me share my screen first.
Okay.
Yes. So today's talk is a WK versus resurgence in semiclassics. This talk is based on these two papers, this one and this one. Okay, let's start. So in physics, there are two resurgence, or you can say two Stokes phenomena. The first one is P-NP relation. This is basically calculated by partial integral method and focused on some physical quantity. And to calculate such a physical quantity, we always use productivity expansion like this. And using Borel summation of productivity part, we can obtain the information of non-productive part here from the Borel ambiguity or productivity part. This is called P-NP relation. And the other resurgence is Exact-WKB method. This is focusing on Schrödinger equation and consider its monotomy by using Borel summation of the wave function. So both use Stokes phenomena and Borel summation, but this one are a bit different story. So there is a naive question: how are they related to each other? And also there are other fundamental problems. So in physics, there are many quantization methods. The most old one is this one, Boson-Fret quantization, and Schrödinger equation, and the modern one is partial integral method. And Gutzler-Trace formula, this is like between Boson-Fret and partial integral. So indeed, there are several quantization methods, but can we derive partial integral method from Boson-Fret quantization? And we know there are Stokes phenomena in partial integral. So can we show the Stokes phenomena in Gutzler-Trace formula or other quantization method? And also, to determine the intersection number of research symbol is very difficult problem, especially in the case of partial integral. This is functional integral, so the number of integration space is infinite. So to determine the intersection number is very difficult. Or you can say to determine relevant saddle point is very difficult question in general. So today's talk, we focused on these problems. And the contents are as follows. First, I'll review the basics of the WKB. And after that, I explain how to connect the different quantization method using resurgent method. And after that, I explain the case of double wave potential and also higher genus system like triple wave potential, and also the case of S1 quantum mechanics like particle on S1. And finally, I explain how to calculate the intersection number of research symbol from Exact-WKB method. This is the flow of my talk. First, we consider Exact-WKB method. So start from Schrödinger equation. And when we use Exact-WKB method, we can obtain exact quantization condition. And this D is actually corresponding to Fredholm determinant of the system. And this exact quantization condition is essentially same to a Boas-Marfet quantization with non-partitive part. And taking logarithmic derivative of this D, then this G becomes the trace of resurgent of this system. And this G is actually gives the Gutzwiller trace formula of the system. And after that, when we consider the inverse Laplace transformation of this G, then we obtain the partial function Z. And calculating the residue of this integral, then we obtain the spectral summation form of partial function. And without calculating the residue, but expansion this logarithm part, then we obtain the path integral form, or you can say transseries form of partial function. This is a flow of my talk. First, I quickly review the Exact-WKB. I think the audience is already familiar with this one, but so just briefly, consider this Schrödinger equation and consider this ansatz to solve this equation. And then the Schrödinger equation becomes Rickert equation. So using this expansion, we can express our WK wave function as like this using S ought. And when we consider the leading order of S ought, then this WKB wave function becomes the WKB approximated form of one. But of course, we consider not approximation, but exact one. So using, we use this one. And now I choose the integral constant here as a turning point, which satisfies this Q equal to 0. And to consider the monodromy wave function, we draw a Stokes curve. The Stokes curve is defined as the leading part of WKB expansion. And this is the simplest one, the Rayleigh's case. Yes, like this, when we across this curve anti-clockwise, then the WKB function becomes like this. And here, the Stokes curve has index, which means which WKB function, I mean, psi plus or psi minus is exponentially grows or not. I mean, in this direction, psi plus is exponentially grows, but psi minus is exponentially decay. So in general, such the ARA type Stokes curve, more precisely locally ARA type Stokes curve, then the modeling matrix can be written as follows. So just multiply this matrix, then we can calculate Stokes phenomenon of wave function. And when we consider the two Stokes graph, I mean, begins from the different turning point, then we have to change the normalization of the wave function as follows. Yes, the wave function normalized at A2 and A1 is related to like this. So this matrix is defined for one turning point. So if there are other turning point, we have to multiply this matrix first, and after that, multiply this modeling matrix. And yeah, this factor is called Boltzmann barrier. This is a key quantity of the lateral calculation. I suppose this example is already given by Dr. Goksha's talk, but just to recall his talk, let's consider the harmonic oscillator. Then Stokes curves is like this. So there are two turning points because here the potential is like this. So consider the analytic continuation of wave function from here to here. We are across the two Stokes curve. So first, multiply in plus and changing turning point. And after that, again, multiply in plus. And finally, we change the normalization to the beginning point. Actually, this is optional. We can omit this factor. Then the final result is this one. In this case, in this direction, at minus infinity, the index is minus. It means psi plus is exponentially decays. So this is suitable function. And after that, in this direction, psi minus is exponentially grows. Therefore, this psi plus becomes like this. And psi minus is exponentially grows. Therefore, to normalize the wave function, we have to impose this quotient should be 0. It gives a quantization condition. And in this case, this condition is equivalent to this one. And in the case of harmonic oscillator, this S naught is actually asymptotic expansion of H bar, but when we calculate this integral, only the leading part can contribute to this one. Therefore, this integral becomes this one, and it becomes this result. This is nothing but the spectrum of harmonic oscillator. Yeah, so far is just recording previous sessions. From here, I explain how to connect this result to a semiclassical analysis of partial function, path integral method. As I said before, the exact quantization condition D is actually regarded as a Fresnel determinant because the zeros of D is nothing but spectrum of the system. And of course, by definition, the zeros of this Fresnel determinant is same to the spectrum. Therefore, the exact quantization condition should be proportional to the Fresnel determinant. So, and the trace of resurgence G and this D is related to this equation. And also this G and the partial function are related to via Laplace transformation and the inverse Laplace transform. This method is motivated by Jean Justan's calculation. Actually, this is just inverse procedure of his calculation. For example, when we use the harmonic oscillator's exact quantization condition, then here is D, and the partial function should be obtained by this integral, and this is easily calculated by a residue theorem. And I remark to calculate this inverse Laplace transformation, we have to choose our integration contour, and in this case, we have to impose the energy should be greater than 0. This condition is actually already yes. To write our Stokes curve, we have to impose this condition first. Therefore, to satisfy the condition, we choose integration contour like this, and pick each pole. Then we obtain the partial function directly. Therefore, using this method, we can calculate the Poisson function directly from the exact WKB method. And also, not only Z, but G, the trace of resurgent has important property. This G can be written in this form. And this is actually the Gutzwiller trace formula of the harmonic oscillator. And this factor is called Master index. I suppose some audience are not familiar with Gutzwiller trace formula, so I explain what it is first. Yes, the trace resurgent can be expressed as the summation of this cycle, one precise classical orbit. And this PPO stands for prime periodic orbit, which is defined as a topologically distinguishable orbit in Gutzwiller's paper. But the meaning of this PPO is a bit obscure because we don't know how to determine this PPO in general. And also here is called master index. More precisely, master index is a number of negative eigenvalue of this fluctuation operator, and the quantity expressed as nu. So this factor is like not master index, but like master phase. However, from here, I call this phase factor also master index. And recalling the previous result, and yes, and if the system has only one type of prime periodic orbit and the constant period and the constant term of fluctuation operator, then we obtain this result. And this form is actually almost equivalent to the previous one. Yeah, this one. Actually, this is a much more exact form. And by definition, this G is a trace of resurgent. Therefore, the pole of G is same to the spectrum of the system. And therefore, the pole of this function is given by this equation. This is nothing but Poisson-Marfret quantization. So essentially, this Gutzwiller trace formula is same to Poisson-Marfret quantization, but the reason why the result is very simple, the result becomes very simple is just we consider harmonic oscillator. When we consider much more non-trivial potential, then the number of prime periodic orbit are much more larger. Therefore, the result should be much more complex. And the problem is the way to determine such a prime periodic orbit in general potential is not so clear. And also, what is the Stokes phenomenon of this Gutzwiller trace formula is not so known. But using the WK method, we can show how to determine this prime periodic orbit and also the Stokes phenomenon of this trace formula. Okay, so let's go to the double potential and also after that turbulent potential. In the case of the double potential, remarkably, the Stokes graph, more precisely the topological structure of Stokes graph changed when we change the imaginary term of h bar like this. When we set the imaginary term of h bar equal to 0, then these two Stokes curves connecting each other and like this. And from this change of topology, the exact quantitative condition also changed like this. And A and B and C is defined like this. And this A cycle and the C cycle is just inverse of the other one. And the B cycle is proportional to this exponential decay factor. And as I said, the result looks different. However, if it takes a Borel summation of this exact quantitative condition and using our formula called DDP formula, this is given by like this in this case, we can show the two different, naively different exact quantitative condition D are actually equivalent. And we obtain the D, so we can calculate the Goodchild-Rest formula directly. Okay, just taking the logarithmic derivative of D, so we obtain this result. First, the perturbative part here and here is symbolically same to the harmonic oscillator. And non-perturbative part is given by here. And the physical meaning of the non-perturbative part is easily get from this picture. First, this quantity is a unit of one non-perturbative cycle because, yes, and this quantity is expressed as like this. And the physical meaning of this form is for one B cycle, or the infinite number of A cycle, this one are attached. And this quantity is our fundamental unit of our non-perturbative part. And after summation, this quantity, and also consider the Maslow index, and counting again the infinite number of this unit, then it becomes a non-perturbative part of G. And also, the Stokes phenomena of Goodchild-Rest formula is changing of direction of A cycle. Yeah, here and here. So when we change the imaginary term H bar, this A cycle, the direction of A cycle is changed. This is a Stokes phenomena of Goodchild-Rest formula. And this change is corresponding to the change of topology of Stokes graph. Okay, then after we obtain the Goodchild-Rest formula, so from here we can calculate the Pareto function or W potential directly. Just consider the inverse Laplace transform of G, then we get this form. And actually this result is nothing but trans series because this B is proportional to this quantity, I mean the baryon amplitude and the summation. And this power is corresponding to March baryon contribution. And using DDP formula, we already know the D plus and D minus are actually equivalent. I mean, there are no Borel ambiguity. So we can conclude D plus and D minus are equivalent, or you can say there are no Borel ambiguity. This is the resurgence claim of PNP relation. So this claim is naturally proved by using DDP formula and this method. And this is just symbolic form, but we can go to much more a physically friendly form using this identification. When the system is just harmonic oscillator, then this omega is just a constant. But in general potential, this omega is not a constant but function of E and H bar. And in the many case, this is asymptotic series of H bar. And using this identification, then this quantity is here is a fundamental unit of non-particle over each baryon part becomes this form. I note from here, not from here is very easily, but from here to here is a neat or bit technique. After my talk, Kamata-san explain how to derive this from this symbolic form to this form much more in detail. Anyways, this form is so-called quasi-modular integral form, and here it's called phase ambiguity, which is corresponding to the Stokes phenomena of quasi-modular integral. The quasi-modular integral is given by this integral. I suppose this form is familiar with physicists. The partial function is given by this one. This beta, this linear beta is corresponding to the zero mode moduli. And this B is baryon amplitude. And this quasi-modular integrals is the interaction potential between instanton and anti-instanton. And when we consider not only one baryon, but multiple baryon, then we have to impose this constraint to satisfy the periodic boundary condition. And calculating this quantity, then the quasi-modular integral becomes this form. So comparing this result and using this function and substitute it into here, then we can get exactly the same form of quasi-modular integral. Therefore, using this method, we can obtain the path integral form of partial function directly. Yes, and also, especially, this GAN function is coming from this integral, quasi-modular integral. But this GAN function is basically coming from this factor. This factor is the part of the Gutzwiller-Trace formula, where you can say the infinite number of times of this part of the cycles. Such the part of the cycle gives this GAN function. Therefore, it's essentially the quasi-modular integral is same to the perturbative fluctuation from vacuum. This is non-trivial physical relation of quasi-modular integral. And this result gives much more non-trivial result, non-trivial claim. First, we can obtain this Freihorn determinant D from the Exact-WKB method, and it's equivalent to we can calculate the partial function exactly. And using DDP formula, we can calculate the Borel ambiguity of both multiplier exactly without any approximation. And also, the perturbative part of Freihorn determinant is characterized by this factor. And this is, when we obtain this quantity, then it means we can obtain the perturbative part of the partial function. Therefore, if we can get the exact form of the partial function like this, by using a Feynman diagram or some other method, then we can identify the function form of A from it. And using DDP formula, we can identify the function form of B from this equation. And we already know the symbolic form of partial function. I mean, in terms of Morse multiplier. Therefore, we can recover the complete partial function from only the part of the part of, or the part of part. Therefore, indeed, we can recover, yes, non-partitive contribution exactly from the partitive information. And the previous method is also valid for any potential. For example, not only a genus 1 system, but higher genus system like trivial potential, then the Freeform determinant becomes like this. The meaning of this structure is also easily obtained. This is baryon contribution, and attached to infinite number of S cycles, it becomes a quasi-modular integral. And also, this is 2 baryon, but not this 2 baryon is distinguished by just rotating 2 here, because the number of quasi-modular integral is different. Anyway, in this case, the non-partitive contribution is represented by this quantity. And from this expression, we can calculate the partial function directly. And the Maslov index of non-partitive cycle is here. Actually, this factor, the Maslov index, has very important role in a reflective symbol decomposition. I'll explain it later. Yeah, so far we consider the ordinary Schrödinger equation, but from here we consider the S1 quantum mechanics. I mean, the wave function defined on a circle. For example, when we consider such a Mashu equation, and in this case, the boundary condition is given by this one. This theta is Bloch angle. So this condition is actually expressed as like this, because here is x and here is x plus 2 plus. So analytic continuation of the wave function gives this modeling matrix, but after the analytic continuation, then wave function obtain this phase factor. Therefore, this equation is nothing but the eigenvalue equation of modeling matrix M. Therefore, to satisfy this condition, we have to impose this condition. Actually, this gives the exact quantity condition in this case. Explicitly, the D shows this form. And the physical meaning of this D and the Gutzfeld's formula is almost obvious. The partly part here is same to harmonic Ostert's case, and the non-partly part is this one. K is given by this one. And the meaning of this K is, first, consider one B cycle and attach the infinite number of A cycle. And to be periodic for one B cycle, then this A times or any or A power n gives a yes, this cycle satisfies the periodic boundary condition. However, in this case, because here and here is identified, so such a trajectory is also a periodic solution. But to satisfy this condition, we have to calculate such trajectory. Then we have to add square root A additionally here. This square root A is appearing from here. And so you can say this quantity is like baryon contribution, and this quantity is instanton contribution. And instant contribution has this theta angle. Actually, this is a topological charge of instanton. And the Stokes phenomenon is same to the case of W potential, just inverse of perturbative cycle. More generally, not only 1 minus cosine x, but 1 minus cosine nx. But the quantity condition is easily given by this one. Just multiply this model matrix like this. In this case, the exact quantity condition becomes this form. Yeah. Importantly, when we set theta equal to pi and n equal to 2 integer, then the result becomes like this. This square perfect indicates all energy eigenvalue or degenerate, or you can say Kramers doubling. This is nothing but the phenomena from the two-foot anomaly of the symmetry and charge conjugation. So we can analyze such the property of anomaly from the Exact-WKB method.
Naohisa, are you there? So is it just me or has it stopped for everyone?
It stopped for me as well. It's Michael Berry.
Okay. It's already recording. If you
Already recording, okay. Okay, when we consider not ordinary Marshall equation, but this potential, then the Fullerton determinant is given by just changing this factor, just multiplying model matrix further. And importantly, the result is factorized for each p. And when we set theta equal pi and this n is an even number, and then this Fullerton determinant becomes a square perfect, which means all energy eigenvalue are degenerate, and which means a two-foot anomaly of the system, more precisely ZN symmetry and a complex charge conjugation symmetry of. So we can analyze such we can analyze anomaly or such topological information from this Exact-WKB method, not just calculating the energy eigenvalue. And of course, we can calculate energy eigenvalue to when we solve the D like this. Actually, yeah, just solving this equation, then we can obtain the energy eigenvalue directly. And of course, when we set theta equal pi, then here and here vanished. So these two factor becomes identity. Then the energy eigenvalue or degenerate. So to obtain this functional form of D, we need a bit complicated calculation. So the next talk, Komata-san talk, will be explained in detail. So we obtain the D, so we can calculate the partial function directly. The result is this one. First, this Q and K is topological charge, or you can say the number of instanton. And K is the number of baryon, or neutral baryon. And the partial function is expressed as this summation. And this quantity, I mean, the unit is written by like this. This F is a hypergeometric function. So this is a symbolic form. So if you want to consider the resurgent structure of partial functions, then just apply DDP formula for it. And if you want to know the quasi-modular integral form, then just using almost same procedure to the previous calculation, that we can get this result. Here in the quasi-modular integral, and this is baryon. And this is phase ambiguity term. Yeah, for example, when we set K equals 0 and Q equals 1, it becomes instant amplitude. So here is square root. Then this SB is a baryon action. So it becomes instant action. And when we set Q equals 0 and K equals some integer, then it becomes March baryon contribution. And phase ambiguity terms depends only the baryon, and the number of baryon, not instanton. And using DDP formula, we can show the resurgent structure is closed in each topological sector. I mean, this partial function is given by the summation of Q and K. And after summing up all K, then we get this form. Then using DDP formula, we can show this quantity has no Borel ambiguity. I mean, the resurgent structure is closed. This result is nothing but a resurgent triangle in terms of Jared Dan and Mittat-Unzars. So we can prove the resurgent triangle without any approximation using this method. Okay, after that, let's go how to calculate the intersection number with the sim. First, in general, the partial function was some physical quantity can be written as this function integral. And as we know, these function integrals can be expressed as the trances or part of the expansion for each other point. And its Borel summation is actually same to the integration on Lefschetz symbol. And this n sigma is called the intersection number of Lefschetz symbol, which determines which saddle point is relevant or not. And the trace or resorbent G is just calculate this Laplace transform, and the Laplace transform is linear. So again, we can get this form. And the Fredholm determinant D and the trace or resorbent G is related to this expression. Therefore, this intersection number appears here, the power of this D. And this sigma is stands for a Fredholm determinant for each symbol, or you can say each saddle point. For example, in the case of double Borel potential, the Fredholm determinant can be expressed as this one. And here as coming from the part of the part, I mean, from two vacuum of W potential here and here. And here is coming from the multi-volume contribution, this quantity. And this power is nothing but mass of index, or more precisely mass of phase of a Kutzler-Trace formula. Therefore, the mass of index of non-particle cycle is exactly same to the intersection number of rested symbol. So we can calculate the intersection number directly from Exact-WKB method like this. And this result is almost same in the case of triple Venn or higher genus system. When we going back to triple potential, yeah, this is the result. These three terms are coming from the three vacuum, and this quantity is coming from our merge non-particle contribution. And here is mass of index is actually becomes the intersection number rested symbol. Yes. Okay, summary. So we show how the two resurgence or two Stokes phenomena are related to each other. I mean, the Stokes phenomena of PNP relation and is regarded as the change of topology of Stokes curve. And using this method, we can show the cancellation or ambiguity of partial function without any approximation, because the exact quantization condition is exact. Yes. And we show the relation, hidden relation between mass of index and intersection number and how to determine it. But this is only valid for one-dimensional system, only one-dimensional Schrödinger equation. And also, we can see the Stokes phenomena of Schrödinger equation and Boas-Mumford, Kutzler, and path integral in amongst such several quantization method. And also using DDP formula, we can recover the complete partial function from the part of the part or partial function. Yes, this is the result of my talk.
Okay, thank you very much. So, is it okay for you to finish it?
Yes.
Okay, so thank you very much for that beautiful talk. And so we now open this session for the questions and discussion or comments. So
may I ask one thing?
Yeah, sure.
Yes.
I would like to understand more on the relation between path integral and your Exact-WKB method. Perhaps page 45 or something, you mentioned the d sigma at each saddle point. I can understand dE on the left-hand side. What is d sigma E? Can you define what object is it?
Well, the meaning of this sigma is, okay, maybe when we consider this quantity, so this is logarithmic. So this product becomes summation.
Right.
So essentially, so this quantity gives this sigma, but more precisely, in the inverse Laplace transform of this quantity gives this sigma, and the meaning of this sigma is trivial, right? This sigma is defined by the path integrals of each saddle point.
I see. So DE has another meaning of having this in terms of H, operator H, but there is no such meaning for this D sigma. You just should refer to the contribution from the saddle, each saddle to the partition function. Is that the way?
Yes, but in the for some case we can, okay. This is Stokes curve W potential, and when we consider this analytic continuation, not like this, then this red line gives this red line gives this factor here. And this is actually the sigma of one vacuum, because yes, for here is coming from here. So in the case of part of the part, this the sigma is defined by such complex domain of analytic continuation to complex plane. And I suppose such trajectory is corresponding to the domain of field xt. This xt is the field value of path integral. So to determine the direction path integral to complex plane like this, not real axis, then it gives such that each d sigma. But this verification is valid for part of the part. For the case of non-part of the part, it looks like this, maybe. I mean, this analytic continuation is here and here and here. However, this blue line, just considering this blue line, it doesn't gives this d sigma directly.
I see. So so not in terms of operators, but in terms of the analytic configuration in this plane.
Yes, yeah, domain of X, or you can say.
Okay, I see. Okay, thank you.
We've got comments from Professor Andre Voss. So now could you see the chat?
Let me see. Sorry, no.
Oh, you cannot? So there is
Where can I see the comment?
Chatting part. So
okay, then may I stop the broadcast?
Well,
okay.
Shortly.
Okay.
Then I can see. Okay. And possibly because one by Chiba-Boré transform. Yeah, actually, it has this Boré transform because For example, okay, this is easy. This A and B is defined by such quantity. And this is generally the asymptotic expansion of H bar. And the correct partial function is the Borel summation of this quantity, like this. And this Borel summation is, the Borel sum means the, Borel summation of this H bar term. So, yes. Is it answer to your question?
He also asked what the Borel plane for you is. So
This Borel summation, the Borel plane is, defined by this H bar.
Oh.
I mean, this S plus is like this. No. So S plus C is like.
I see. So now he gave back some more comments.
Okay. Well, why can I see? It's quite, anyways. The spectrum, the consider functions, operational function, which are natural boundary.
The spectrum square has partial function, which is natural boundary.
Boundary means the boundary of Borel plane.
He said yes.
In this case, there are no such boundary term on the Borel plane, I think. H bar is valid for any value. Okay, okay. So in this case is related to S1's case. Yeah, so when we consider this S1 quantum mechanics and when we set almost free case without potential, then the spectrum is like n square. such a case, but in this case, this is free, so we can't draw Stokes curve. But I'm not sure this is answer of your question, but to calculate the Python function, we have to calculate Bromwich integral like this, or inverse Laplace transform. This one. And this integral is often become like this. However, in the case of periodic potential, for example, the audience Marshall equations type, then this potential is bounded upper and below. So this integral counter are fixed at some point, not go to infinite. But I'm not sure it gives a boundary of for a plane.
Okay.
Sorry, I can't give a good answer to your question.
If you have some more questions, please ask him. Feel free to ask questions or give comments.
Can I ask a question?
Yep.
So at the beginning, sorry, Andre, I think you still wanted to continue.
Okay.
Perhaps I can read it to you if you want.
Okay, please.
I would just better understand if I could see what is the Borel transformation that works for you. But of course, you may answer that later. Thanks.
Yes. As I said, the partial function is given by such a Borel multiplier. And this Borel multiplier is asymptotic expansion of H bar. So this the partial function is also the asymptotic expansion of the H bar. So the Borel transform and the Borel summation is here for the H bar term. Actually, Borel summation is homeomorphism, so we can show the well, which one is easier to see? Yeah, of course, in general, such this quantity gives the Borel summation product of Borel multiplier gives the product of Borel summation of each each part. And of course, Borel summation has this property. So if the Borel summation of each Borel multiply is defined, then the Borel summation of partial function is also defined directly. Is it sufficient for your question?
Perhaps while we wait for a chat answer. Do you mind if I ask a question in the meantime?
Okay.
So I just wanted to know, so you had some explicit formulas, like so expansions at the beginning, and I was just wondering how easy it would be to meaning you've shown the partition function and expansion in saddle points.
You mean the
at the end,
flowchart?
towards the end, I was just wondering how easy it would be to transform that to explicit formulas in the sense of in the sense of actual expansions. So
for example, this is a partial function.
So meaning, so you're integrating over DE. You have the cycles, so you can, in principle, just could get this an expansion in beta, or
this B and A is some expansion of H bar.
Yep.
Like this, where A is also 1. So this quantity is part of the expansion of H bar, and also this B. Actually, B is like the leading part is bion, and some H bar correction term.
Okay.
So this is, trans-series form of partial function. So if you want to calculate this quotient, then just using a Riccati equations relation, because we already know the definition of S odd, or you can see the Borel multiplier, order by order. So using that Riccati relation, then theoretically we can calculate all quotient. But just theoretically, so practically to determine such quotient is a bit difficult. So after my talk, Komoda-san will be explain some effective method to calculate such quotient.
So, but then, okay. And then you have, and so with the B, then you'd have the non-perturbative part, you'd have different exponentials, I guess, not just the leading one, because you'd have the B to the N.
Yes, so this is March bion contribution, not single bion.
Okay.
And this integration, E, is coming from delta function in terms of physics, this one. This delta function becomes actually this integration, and this S is essentially same to the E in this expression.
Okay. So Andrei Foros wrote that he still have points. I still have points to understand. It would be nice if you could give a reference, and I'll be glad to chat with you in some days. Thank you very much.
Okay, you're welcome. Yeah, references here and here.
May I ask a question somewhat similar to Ines? Is it okay?
Yes, please.
Perhaps going back to page 30, you have, for example, sum over infinite number of n. Presumably, this means that there are infinite number of non-perturbative exponentials hidden here. So my first question is that is it always the case that this sum over various saddles, that is a sum over various non-perturbative exponential, is convergent series?
Well, this summation is convergent because this summation is coming from this logarithm.
Mm-hmm. How about, suppose we start from the path integral. There are a number of saddle points, and apart from this trivial vacuum, we have presumably infinite number of saddle points. And my question is whether the sum over contributions of non-perturbative saddles, is it convergent?
Here, I mean, this is the calculation. I mean, B is 1 baryon, so this summation is summing or such the infinite number of baryon contribution. And here, 1 over n, this factor is coming from cyclic permutation of multi-baryon contribution.
I see. So at least in this class of quantum mechanics problem, the sum over the perturbative series is divergent asymptotic series, but after Borel resummation, each contribution from each saddle can be summed in with finite radius convergence. Is that the case?
Yes.
Okay, that's nice. Okay, so another, let me confirm my understanding. I understood from your formula that for example, your one type of Morse multiplier A contains all the information of the perturbation series at, say, trivial vacuum. And the B contains all the information of connecting trivial vacuum to other non-trivial saddle. And together, you can get everything. Is that the way?
Right.
Okay.
Yes, more precisely, if we can obtain the complete information of A, then that's enough because of this DDP formula.
Right, right. Okay, I see. Okay, okay, thank you very much.
So may I ask questions?
Okay.
So did you assume the turning point of your potential is real, or you can make it in complex valued?
In this calculation, real. Indeed, when we consider higher energy like this, then here is here are two complex turning point.
Yes.
This is coming from, because the Stokes graph depends on the energy.
Mhm.
So it may cause some problem. However, when we, actually this is related to the next torque, constant torque.
I see.
When we consider not ARA type is a WKB, but degenerate Weber type is a WKB method, then this problem is solved. And also we can connect this ARA type calculation and degenerate Weber calculation directly.
So I'm wondering, in such a case, how to distinguish A cycle and B cycles for generic
In this case,
potential?
this exponentially decay or not.
Uh-huh.
I mean, in this case, okay.
Like a cubic potential, right? For example.
Cubic potentials and Stokes curve is,
But anyway, you like it.
maybe like this or something.
Yeah.
So this is in this case, and when we consider like this, then one then becomes complex. For upper one is fine. And in this case, we can already define both multiplier by defining such cycle. Even if there are, the turning point on complex plane, and in the case we can identify which one is exponential decay or just phase factor by calculation. But of course, this is just for ARA's case. In the case of degenerate Webers, such problem doesn't occur.
Mhm.
I mean, in the case of degenerate Weber potential, Stokes curve doesn't depend on the energy. And
I see.
we can set
So-
all turning point real.
So there's no potential problem for any type of generic potentials, such that to my understanding, there's no problem for any potentials. Do you have any problem for arising?
Actually, little bit, yes. But
Yeah, maybe I should ask
yeah,
Kamoto-san. Yeah.
yes.
Okay.
But this procedure, I mean, calculating the Poisson function with this method is valid for any case. The problem is to verify the function form of the Poisson function, not symbolical.
So in generic case, the eigenvalue could be also complex, not real ones.
Yes. For example,
So
when
in that-
consider the cubic potential, so in such a case, we have to change the analytic continuation. I mean, okay.
So in that case, Gatsby formula is still valid.
Valid, yes.
Okay.
Yeah, like this or something.
Okay, thank you very much.
This point, shall we thank Naohisa again and stop recording, perhaps?
Yeah, I think it's better.
Well, thank you so much for the talk and for the discussion.
Thank you.
We will stay on, but just press the stop the recording at the moment.
Mhm.